I'm gonna start. Okay. So we're just gonna do a quick review on. Oh, I already did my pull request. I hope they accept it soon. So okay, so we're gonna do a quick recap on the recurrent neural networks. So we saw that classic neural networks, they have a fixed size vector as an input and they produce a fixed size vector as an output. So, and they also assume that the inputs and outputs are independent, not from each other, like it's not that the output is independent of the input, but in the time steps, if we have one output, the next output is going to be completely independent from the previous one. But recurrent neural networks, they allow us to operate over sequences of vectors. So we have sequences in the input and sequences in the output or both. And they are trained using sequential or time series data. So in this case, we're gonna see that prior elements are gonna affect the output of our next sequence of steps. And we also mentioned that we have a structure that it's called a recurrent unit. And in this case, the output from the previous neuron is going to be connected to the input on the next one. And recurrent neural networks have this hidden vector that's called the recurrent unit, and this hidden vector is going to be updated at each time step in our training process, and it's going to serve as a memory that is gonna be based on both the current input and the previous hidden state. So it's only a hidden layer, it's only a hidden vector, and the recurrent neural network use that hidden vector to kind of remember what they saw in the previous time steps. And we also mentioned that they have some problems. We can see here, like right here, the B will be the hidden vector, and because we have this feedback loop, another way of looking at this architecture will be like unfolding the connections between the neurons, and in this very small example from StatQuest, we see that in this case that V vector will be this W2. This one is going to be the vector that connects one neuron to the next one. So yeah, it's a structure where our networks are connected. And when we're doing the training, as we already mentioned, we use backpropagation, and backpropagation uses the gradients and with partial derivatives, and that translates into tons of multiplications. So when we have weights with values less than 1 for that hidden vector, that will mean that upon many multiplications, the value of that specific element in the vector is going to become very, very small. So that's called the vanishing gradient, and it limits the ability of the network to learn long-term dependencies. And if the value of that weight it's greater than 1, that problem, it's called the exploding gradient, and that's gonna affect our training process, and it's gonna be really hard to find the actual minimum of the cost function that we were talking about last week. So yeah, that was a recap of the of chapter 8. And now we're gonna see LSTMs networks. So LSTM is short for long short-term memory nets. And there are also recurrent neural networks, but there are kind of a special kind of recurrent neural networks. And they are capable of learning long-term dependencies, so we're not going to see the vanishing gradient problem in these kind of networks. And they were invented by these two scientists whose names I cannot pronounce in 1995, and they actually became the default choice for recurrent neural networks. Actually, in one of the resources that our handbook has right here. Oh, sorry. No, it's actually in this one. The author starts talking about recurrent neural network, but he goes to LSTMs like very quickly. So it seems that they've been they are actually very popular, and we can see like in this very small example a relationship to what I was talking about, the vanishing gradient. If we would like to predict the words, if we have some text and that's going to be our sequence input, and we would like to predict the words in orange, this. So our text says, Alice is allergic to nuts. And then we have some sentences, and then we have this sentence that says she can't eat peanut butter. We have the context of peanut butter in the fact that in the statement that this sentence mentions that the fact that Alice is allergic to nuts. But if we will have like many sentences between these two facts and between the context that our neural network has to pick to actually be able to predict these two words, if we have many sentences between them, the context will be lost because of the vanishing gradient problem. So the neural network won't be able to predict these texts. So yeah. So now we're gonna see the structure of the long short-term memory networks. So they are also a chain-like structure, just like the classic recurrent neural networks, but the difference is that they have 4 modules instead of the simple hidden layer, simple hidden vector that the RNNs have. The 4 modules are called the sales state, the forget gate layer, the input gate layer, and the output gate. And this is the structure of the of the network. We're gonna review each of the modules, but yeah, we can see right here that it is also a chain like structure, and that one neuron is, well, the yeah, so the steps in our sequence are also chained like in the recurrent neural networks. Okay, and as we can see here, this type of neural networks, they use 2 different activating functions. The sigma function that we already reviewed, and the tan-h function that we're gonna review in a moment. Is hyperbolic tangent, right? I think it is. Yeah, hyperbolic or tangent hyperbolic, but it's tan-h. Okay, so these are the 2 functions, and the difference between them is that the sigma function, as we already reviewed, it accepts real numbers, and it outputs something in the, again, like a number in the range of 0 and 1. And the tanh function, its output is gonna be between -1 and 1. And we're gonna see now the first gate, the first model of our long short-term memory network. So this line, it's called the cell state, and this is gonna represent our long-term memory. And what it's gonna do is just that it's gonna pass vectors. We have no weight here. We have no activating functions. It's just it's just like two very like very simple operations. One is a multiplication, and the other one is an addition. So it only passes vector without weights. And during each time point, the network is gonna either remove or add information to these cell states. So this is what is gonna be like holding what the memory of the network. So what we're learning during each time step. And to add or remove things from the cell state, the first model that we see is the forget gate layer. So the forget gate layer, its input is gonna be the output from the previous time step, and this gate is gonna decide what information we're keeping from the previous output. And it's gonna use a sigma function, and we can kind of like traduce the output of that sigma function into saying, okay, if we get a 0, we're gonna completely forget this part of the information that we got from the previous output. And if we get a 1, we're gonna keep this. So that will be kind of like the first operation in our network. We're gonna first decide what are we gonna keep from the previous output. Then we're gonna have the input gate layer. In the case of the input gate layer, we're gonna have its input is actually the input from that time step, and not the output from the previous one. This gate has the sigma function again, and it also has the tam function. And what the tam function is gonna do, it is gonna help us create a vector of new candidate values with the -1 to 1 range in the output. So those candidate values are gonna be like a potential memory to add to our cell state. And those values from our tangent function, they're gonna be paired with values in the sigma function, and the values from the sigma function are gonna decide what percentage of that potential memory are we gonna add, again, from the 0 to 1 range. And yeah, so we have here like a combination of these two activation functions. And as you can see here, this output, they're merged. The output from the sigma and the tanh function are merged using a multiplication. So with that, we're gonna update the cell state. So with the output from the previous time state, we're gonna decide which things do we wanna forget from the cell state, and with our candidate values from the new input, and their associated scaling values from the Sigmund function in the input gate, we're gonna decide how are we gonna update the values on our new cell state. Okay, so that's the function of the input gate, and combined with the previous one, with the forget gate. And we finally have an output gate. So now that we have updated our cell state, again, we're gonna have a tan h function and another Sigmund function combination that is gonna say, okay, we already have this cell state, so how much of that cell state are we gonna pass to the next output? So this gate is gonna help us filter the cell state that we have, so that we can create a new short-term memory, and that's gonna be the output of our entire unit. Is I don't know if there are any question. No, any comment?
Nothing so far, but thank you for presenting this.
Okay, yeah, just a clarification. We have like each of the elements in our chain link structure is gonna be associated to one of our time steps, meaning to one of our sequencing input.
I do have one question.
Yeah,
why doesn't this suffer from the vanishing or exploding gradient problem? Is it because of the sigmoid normalizes it between 0 and 1, or
yes.
Okay.
Yeah, I mean, because it normalizes to 0 and 1, and because you update that cell state during each time, yes, during each time step, and it is not only because in this case, in this case, the weight was the same for the entire chain. So in the case of our cell state, is not gonna be a single weight for the entire sequence. We're gonna be able to select which part of the information is gonna be updated, and which part of the information are we gonna keep, and by how much during each time step. I guess we should maybe during the break I will try like coding something and to actually get more practical examples. Yeah. Okay, and finally, the gated recurring unit. So they are a variation of the long short-term memory networks, and they only have two gates. A reset gate that is gonna select how much of the previous state we want to remember, and an update gate that's gonna say how much of the new state we want to copy. They were introduced in 2014, so they're actually a simplification of the LSTMs, because they have fewer parameters, fewer functions. But I read that there is no like a performance difference between them, so I guess people still use SLTMs. And yeah, so that's all I have for these two chapters. Thank you. Oh,
Okay. Thank you, Diana. While we hear folks, were there any more questions about LSTMs or GRUs? Okay, and I believe up next, thank you, David, for sharing your screen. We see your PowerPoint at the moment, and whenever you're ready, go ahead and tell us what you've been looking at.
Sure, yeah, okay. All right, there's some code examples. I didn't write the code, but yeah, I found it and I thought it was a good demo. So embeddings and topic modeling. So these are kind of like two separate topics. Embeddings is probably the one that's more relevant to generative AI. Topic modeling is more relevant to natural language processing. So let's start with topic modeling. Can you guys see this diagram here?
Yes, we can.
Okay.
Backwards.
Yeah, okay. So basically, there's latent variables in text that are not able to be observed directly. And like, for example, the sentiment of a certain text. So for example, if let's just skip to this example, and the first document here, or let's say these 3 bullet points are 3 different bodies of text or 3 different strings. We can see the first one has a certain sentiment. A whopping 96.5% of water on Earth is in our oceans, and so you can see there the kind of mood or emotion in the setting seems to be kind of in amazement or wonder. And so that's kind of an example of a latent variable. In text of a latent, you can't actually see the emotion or measure it directly, but it's kind of inferred from the state of the text. So anyway, now in topic modeling, most of the algorithms don't actually care about the order of the words. It's just treating them as a kind of like a set in math or a set of words, which is called a bag of words. Basically, what that means is that the number of occurrences, the presence of each word is detected, and in some algorithms, the number of occurrences is detected, but the order of the words doesn't matter. And we can try to summarize what a certain sentence or a certain piece of text is about using topic modeling. So just to try to estimate the topic of a certain body of text. It's similar to clustering, if you're familiar with the nearest neighbors algorithm. The difference, however, is that clustering will put different documents into different groups based on some sort of feature. But topic modeling actually gives you the the words that are most associated with the topic, and I'll explain that later. So yeah, we have so the problem is that we have a bunch of unstructured text documents consisting of words, for example. Like, for example, say that you have a library of books and you want to sort them all by topic without reading all the books. Like if you got maybe say a digital library of like 2,000 books and you want to organize them based on their topic. So we want to first establish or determine like a certain word that has to do with each book, for example, or maybe there's a book that's partially on water but partially on ships. So you may want to have a certain indicator of how much it has to do with, water and how much it has to do with ships, for example. And so this is still an unsupervised learning algorithm, similar to k-means or other clustering algorithms, because we don't know the topics beforehand. So we don't need any labels for this for topic modeling. And so yeah, back to this example. So we can see here for document 2, 1/3 of your life is spent sleeping, and sleeping 7 to 9 hours a night each night should help your body heal itself, etc. And so we can see that the algorithm that was used here found that it had to do with these words. These were the most important latent words that had to do with the topic. So still an hour and sleeping. So yeah, this algorithm, you can see it in, it's more of in the machine learning category, and it's not perfect. Anyway, so the solution to our problem from before is to first clean and normalize the data to a standard form, because there's a lot of features of regular text that can mess up our algorithms. And so we want to simplify the text as much as possible so that our algorithms can run more simply and more easily. So we remove punctuation, remove case, or convert everything to lowercase, for instance. And there's also something called lemmatization, which we'll get to later. And we want to count the number of times each word appears in each document, the bag of words technique, basically. And then using the word count in each document, there's two main algorithms that are used for topic modeling to determine the topics. The first one is latent semantic analysis. That's the more simple algorithm. Basically, it depends on singular value decomposition, which I think Derek explained in a previous presentation. And so I'm not going to go into singular value decomposition in this presentation, but the other algorithm is latent Dirichlet allocation, which is more Bayesian in approach. So we're assuming that each document is a collection of topics, and then each topic is a collection of words. And we can assign the words to topics and the topics to documents randomly, and then use a Bayesian network which is different from a neural network, to update the prediction and update the topics, and do that many times until the accuracy stops improving, or some sort of objective function stops improving. There's a few different variations on LDA, on latent Dirichlet allocation. And then at the end, we return a vector representing the main words associated with the document's topic and how much it correlates with the topic. So basically, you can see the end results here. Yeah, here. And so, yeah, this will identify the main topics in each document. So first of all, we have to go through normalization. So we have to remove punctuation and stopper words. So most of the information online I found had just a regular constant list of stopper words, and a lot of natural language processing libraries have a lot of really common stopper words, like articles, for example, the, that, I. Yeah, basically, it'll very bad language. And also, all the punctuation needs to be removed. And I didn't put it in here, but also we need to convert everything to lowercase. And then secondly, we want to perform lemmatization on each word to get its normal and basic form. Lemmatization is actually its own field. It's actually still another open problem. There's machine learning approaches and rule-based approaches for lemmatization. We're just going to go with a more simple approach based on stemming. And so here's two examples. So ran, runs, and running, and run would all be replaced with run, for example. Better would be replaced with good, and every form of a word would be replaced with its simplest form, basically, in order to get the topic. So now here you can see the sentence from before. A whopping 96.5% of water on Earth is in our oceans, covering 71% of the surface of our planet. And at any given time, about 0.001% is floating above us in the atmosphere. If all that water fell as rain at once, the whole planet would get about 1 inch of rain. So basically, whopping 965%. You can see the simplest version. It kind of seems like what it would be if a caveman was talking, or what I imagine a caveman would be saying, or a stereotypical caveman would be saying. So it's kind of hard to go backward. There's some information lost here using the topic modeling approach. This topic modeling was what would be done before deep neural networks were used for natural language processing as much. But yeah, we can see here whopping 965% water, Earth. And so you can kind of get a sense of the topic. And based on that, we can count, it doesn't show it here, but we can count how many times each word appears in the document. And so, for example, water appears several times. So that would have a higher count. And a word like time only appears once. And so it would only have a count of 1, basically. And this is from a different example, but the idea is basically we can create a matrix. So on the top, we can see the different documents. And on the bottom, we can see, we're on the vertical axis, we can see different words. And now you're starting to see how we can use matrix methods and borrow some methods from linear algebra to think about this. So yeah, stopping here, there's a really good animation that I can find. Yeah, I'll just switch to a different screen real quick. So we can see here. Are you guys able to see this animation?
Yes, I think so.
Okay, cool. So we can see here, this is the example from the slide. And just so you know, each square represents the count in the matrix. So a darker square is a higher number, and a lighter square is a lower number. So for example, document 0 talks about pollution and power, and document 8 talks about environmental stuff. So we can use our matrix methods to reorder the columns and the rows in order to find, in order to group basically certain words based on a topic, for example. So yeah, air, pollution, power, environmental, those are kind of clustered together. And legal immigration, amnesty, aliens are together, and then defense, nuclear arms treaty, those are together as well. So it's basically based on what words are in what document together. So yeah, I'll go back to the slides. Yeah, so we are going to use a certain algorithm for that. We're not actually going to use the one in the animation. Well, but this is similar though. So latent semantic analysis will use singular value decomposition to reduce the dimensionality. And so instead of having each document related to a whole bunch of words, we're going to find the most important words that are associated with it. And yeah, we're assuming that words with similar meanings will appear in similar documents. So for example, defense and nuclear, for example, might be in some of the same documents, or environmental and pollution. And so yeah, we construct our matrix and we simplify the data and maintain the relationships between the words and documents. And when comparing the similarity of documents, we have to, for example, compare whether one document is similar to another, like maybe D9. How similar is D9 to D6, for example? We can use cosine similarity, which we have a formula for on the slides back here. So basically, we can take the count of each word in each document. Let's say we have two documents, A and B, and if you ordered all the words, we can in a certain standard order, we can take the dot product, or we can multiply the amount of times it occurs in one document to the amount of times it occurs in the other document, which is in the numerator of this, and we can do that over all the words. So if a word occurs 0 times in both documents, then that part will be 0. But if a word occurs several times in both, it'll be higher. And it'll be divided by this formula down here. So in general, if two documents have the exact same words, then cosine similarity would be close to 1. And if they were completely different, if they shared no words, excluding stopper words, which are removed, then the cosine similarity would be 0. And by the way, are there any questions so far? Okay, no questions. All right, and yeah, we can do singular value decomposition. It's been a long time since I took linear algebra, so honestly, I don't actually understand singular value decomposition since I used it in Derek's class 6 years ago. Yeah, but anyway, so here's kind of a summary. It's a dimensionality reduction technique. So we you can also use principal component analysis and some variations of this algorithm. But yeah, we have our document word matrix, and we do singular value decomposition, which basically involves factoring it into two different matrices, and then finding the latent semantic space, which is another matrix, which will basically associate the most important words in the documents and which ones are similar, I guess. And the result is that the different documents will have a different vector of words, which will be similar, basically, as we saw in the animation. Latent Dirichlet allocation is a little bit different. It's using a Bayesian approach. By the way, I was kind of a little bit hand-wavy of the details of latent semantic analysis. There's a few resources that I can provide at the end, I guess, if anyone has any questions. Yeah. So latent Dirichlet allocation is a little bit more complicated. We're using a Bayesian network, which basically is not a neural network, but it's a statistical model that assumes the documents are made of words that help determine the topics, and the documents are mapped to the list of topics based on what words they have. And so, yeah, the order of words doesn't matter. Only the count of the words in each document. So this approach, basically, the way to think about this approach is basically randomly matching each word to, well, we want to match documents to words and then words to topics. And so we can start by randomly mapping each word to a topic and using a Bayesian formula to update this random guess on each iteration. And there's objective function, and it should initially improve with each iteration. And when it stops decreasing, so when it doesn't get any better, then the algorithm stops. And so instead of, well, yeah, it's a slightly different approach. And so, yeah, I'm gonna go into embeddings. We have a little bit of time. Let me get the tab open. Oh, well, there's another algorithm, word2vec, which is yeah, I didn't actually have time to make a slide for this, but there's another algorithm called word2vec, which I'll talk about now, I guess. Yeah. So word2vec involves finding, basically using a window to count the words in a certain window. And yeah, I didn't make a slide for it. I'll make a slide for it in the next presentation, if that's okay.
While we're here, what did you mean by window? Sentences, paragraphs?
So we use well, to summarize, we use the bag of words technique after doing the initial pre-processing. And by window, I mean a list of words has a fixed length. So you have to specify the length in the input to the algorithm. So the examples I saw were all like 3 words, and it involves finding the count of the words in each window, and yeah, I'll make slides for it on the next presentation. Yeah, I kind of you should probably done this one. But whatever, I'll do it on the next one. Yeah, are there any questions about anything we did cover? Okay, well, just to give you guys an idea of the embeddings.
Yeah, I guess I was curious at the LSM methods, if there's any superiority, if there's one method that's superior to the other. I think there are several generation. I think different methods that have been described for word prediction. So I'm kind of curious if one is, yeah, latent semantic analysis, yes. If one is superior to the other.
Well, I've
I
been looking at
think some like GPTs use a different one. I can't remember what the name is, but just curious if there are what the ranking, if there's one is better than the other, and what's the difference in the algorithms that run behind them.
Yeah, in my opinion, both of these are kind of methods that were used without deep learning. And so, in my opinion, deep learning is probably the most effective method for text summarization or to generate a summary. The bag of words technique, which both these methods rely on, doesn't care about word order. And so it's just going based on what words are in the sentence. And so in my opinion, both these algorithms are going to be worse than deep learning and the LSTMs that were mentioned in the previous slideshow. So yeah, it was in the book, but it's not necessarily the best method in my opinion.
Yeah, I kind of thought it was outdated, but I wasn't sure what you thought about it as well. I did see it in the book, but I was like, you know, I agree with you. I think the deep learning approach is probably better, but I don't know why it was in the book.
Yeah, I think that the reason that this is in the book is because the techniques used are useful for understanding the deep learning algorithms, since they use some of the same techniques, but or some similar techniques, but the algorithms themselves aren't that necessarily that effective in my opinion. Like I was looking at some of the notebooks they have, and they were like, the results actually weren't very impressive, like at all, honestly. I've got a notebook open in one of my tabs. Yeah, I'll find it. Yeah, deep learning is the way to go, basically, is my main point. Yeah, there's a lot of notebooks on this demo. I'll find it, and I guess I'll post it in our chat later. Yeah, the results aren't honestly that impressive. Well, I guess it was impressive for its time, but yeah. Okay, well, so the main idea behind embeddings is to assign a word to a vector of real numbers, and usually using, most of them nowadays use deep learning for creating an embedding, but it's assuming the main problem though is mapping each word to a vector of real numbers, such that all the vectors have the same length, so every word's vector has the same length, and the real numbers indicate the relations between the words and how one word is related to another word. So I've got a notebook for this, which I'll start. All right, the notebook's starting. Okay, cool, and I'll switch to that tab. Okay, cool, it's running right now. This website is Kaggle, by the way. So they have a lot of competitions on basically data science and machine learning. Yeah, so we're gonna load a pre-trained embedding from Google, which is word2vec, using the word2vec algorithm. And so we're gonna be using that. So now each word has a certain embedding of a number of floating point numbers, and the idea is that the words that are similar will be similar in that vector space, and words that are different will be far apart in that vector space. So, for example, if we look at the words that are most similar to king, for example, and we look at the 5 closest words in the vector space. So what this is going to do is it's going to find the vector associated with king, search at look at all the other vectors in the vector space, and find the 6 closest, basically. So kings, queen, monarch, prince, ruler, etc. Now we can also add and subtract vectors. So we can say, for example, king minus man plus woman is the example that is most common. So yeah. So yeah, we're gonna take the king vector, subtract the man vector, and add the woman vector, and get the 6 closest, and the resulting vector will get the 6 closest words basically in the vector space associated with it. And so here they are. And similarly, you can do that with a lot of other words. Yeah, does anyone have anything you want to try in here? All right, well, I tried statistician, but it's not in this dictionary, unfortunately, in this data set.
Just as a shameless plug, if anybody tries this in the next couple of weeks, just put it on a Slack channel because I want my students to try it as well.
Okay. Sorry, what was the first part of what you said?
Oh, if anybody is trying out these nice word-to-vec calculations and you come up with something interesting, yeah, just please put it in the Slack channel.
Yeah, makes sense. Okay. Have you used this word-to-vec thing before?
Nope, I think we're all pretty new to it.
I kind of heard about it from one of Andrej, I think Andrej Karpathy, I think his name is. He used to work at OpenAI. He described it in he was doing a video on the foundation of large language models like ChatGPT and things like that. And he talked about, I think, word2vec. Yeah. So I'm a little bit familiar with it. I didn't get to play around with the word2vec, itself, but I've kind of heard about it to understand how it works.
Yeah, makes sense. The key thing here is that words that are similar will be positioned similarly in the vector space. There's a few other functions in here to show the distance in the vector space between different words. So, for example, I think there's a way to say find the difference between them. Let's see. I don't know if that's an actual function. You know what? I'll look this up later, and maybe I'll post the notebook later. Actually, yeah, we can see the number of dimensions for each model. Yeah, okay. Actually, I think we can just subtract using this model object here. So, for example, let's see, can we do that? Yeah, so we can see that. Well, actually, first, let's just run this university so you can see it's a 300 length vector. And then we can see that the distance between university and college is pretty close, but the difference between university and like Acorn, for example, well, it's not in the dictionary. What's a word that's different from university? Maybe prison. And it's actually kind of similar. Okay, well, those are both places, so I guess they're going to be in a similar area. Maybe like a rain or something like that. It's actually closer. Okay, so maybe I did this wrong. The key thing is that they're supposed to be in a similar position. There's some visualizations using only 2 dimensions, but yeah, I don't know why it's doing that, huh? But you can also use this to find words that don't match in a certain list of words. So like breakfast, cereal, lunch, dinner, the word that doesn't match is cereal. Yeah. So that's that. So there's a lot of cool things you can do with embeddings. Basically, it models the structure of how words are used in sentences. Yeah, that's what I have. Yeah, I guess I could have added more on the word-to-vec algorithm.
Thank you, David. Yes, Word2Vec, as I've been going through the materials and, of course, about to present them to my own students, is very interesting and is great for reaching a wide audience. A note on your calculations, we're, of course, talking about the lengths of vectors, the magnitudes. That's why the code has to handle that as such. And while we're here, and apologies, I'm the one that's been endorsing this pace, and that's why we always feel a bit rushed. But while we're here, are there any questions or more comments for the presentations we saw today?
I guess there one of the questions I sort of had has been how those numbers are generated. Is it like a probabilistic how the weights assigned to each of those words assigned?
Yeah, there's two algorithms. The first one is the word-to-vec algorithm, which I should have made slides on, but I didn't. Anyway, but I'll just show you on the Wikipedia, I guess. So the idea is there's you have a string of text, and there's a window that you want to include the words in, and it's usually, in the examples I saw, it's usually like of length 3, and you figure out which words to include, and there's like something about a count. Maybe you could explain it better, Derek. To be honest, I kind of rushed through it.
In my opinion, the individual vectors are kind of arbitrary, but as you stated earlier, comparisons in between vectors are a cosine similarity.
One more time, please.
If you're comparing two vectors such as king and queen, remember that there is a formula called cosine similarity that measures how far apart vectors are or how close together vectors are.
Yeah, I was trying to get a point you made about random assignment of different vectors, how that works. Yeah,
so the vectors themselves are completely random, but it's only the difference between them that matters, basically. Hypothetically, if you added 1 to every vector in the vector space, you could still use it because the distance between them would be the same. Or if you like rotated every vector in the vector space a certain way, as long as the vectors were the same relative to each other, then it wouldn't matter.
Sounds good.
We are past time, and again, apologies for the rush here. I don't know if you all had a chance to check out the sign-up schedules